Okay, so now we're going to look at hypothesis testing. And hypothesis tests are fairly similar to, they're not exactly the same, but similar to when we did confidence intervals. The idea of a confidence interval was you want to estimate some kind of population parameter. So for example, we wanted to estimate the percentage of the population that would vote for a Democratic candidate in the next election. The idea there was you would take a sample, find a sample percentage, like p hat, and then add and subtract a margin of error to that p hat value, and that gave us an interval estimate for p. Well, with a hypothesis test, we use sample statistics, like p hat or x bar or s, to examine a claim about the value of a population parameter, mu, p, or sigma. Every test has two hypotheses. There's a null hypothesis, HO, and that always contains a statement of equality. Okay, that always has the equal sign. Okay, so the null hypothesis is always equals. So like mu equals 7, or p equals 0.36, sigma equals 1.4. Okay, so the equal sign is always in the null hypothesis. The alternative hypothesis, or H1, sometimes HA, okay, sometimes they'll say HA instead of H1, just depending on the book that you're reading. A stands for alternate, and that contains a statement of inequality, okay, meaning the less than, greater than, or not equal to sign. Okay, and when we do actual examples of these, those setting of those hypotheses really aren't too bad once you get the hang of it. Okay, so just giving a bunch of examples here, state the null hypotheses and alternative hypotheses for each statement, and identify the claim. Okay, so again, the idea with hypothesis test is somebody's going to make a claim about some kind of population parameter. Okay, so for example, a restaurant may claim that a certain sandwich of theirs has less than 5 grams of fat. Okay, so they might say that mu is less than 5. Well, it's not realistic to take every single sandwich that they've ever made, so to get the population value. So the idea is you're going to find an estimate by taking a sample and then calculating x bar, finding the standard deviation. You'll have a sample size for that sample, and then we're going to test that claim that mu is less than 5 or less than a certain value. Okay, so we're going to build up to that, and we'll get to the examples in a later video. Okay, so we're going to focus on the first thing we have to do is stating hypotheses. Okay, so a restaurant claims that a mean wait time is less than 20 minutes. So when you see mean wait time, that means we're looking at mu. So they're trying to claim that the mean wait time of their population of customers, so of all people, wait less than 20 minutes on average. Okay, so the null hypothesis, HO, always has a statement of equality. So that means they're trying, when we write HO, it's mu equals 20. Okay, so the mean wait time less than 20, mu equals 20 will be HO. Well, the alternate hypotheses, you look at the wording, less than, okay, is that. Okay, so mu less than 20, that's going to be the alternate hypothesis, and that's what is being claimed. Okay, so again, once you see an example of these, they're not too bad to set up. Okay, so that's all you have to do in these questions here. Identify the null and alternative hypotheses. A surgeon claims more than 90% of his patients say their surgery was a success. I don't know what the other 10% say. Maybe they can't say anything. Okay, so a surgeon claiming more than 90%. Well, more than 90%, what you're looking at now is a percentage or a p-value, okay, or a population proportion. So there, HO is p is equal to 0.90. And then more than 90%, you're looking at p greater than 0.9. Okay, and that's your alternate hypothesis, which is also the claim. Okay, part C, the college claims that more than 75% of their graduates are employed within 4 months of graduation. Now this one was meant to trip you up a little bit. What they're claiming is that more than 75% are employed. Okay, the 4 months is meant to trip you up. They're claiming that P is greater than 75%. So P equals 0.75 is the null hypothesis, and then more than 75 will be P is greater than 0.75, and that is the alternate hypothesis. Okay, and that is also their claim. Okay, going through these, part D. A secretary claims their boss receives 15 phone calls per day. Well, that's not, 15 phone calls is not a percentage. Okay, it's a number of calls per day, so that's an average. So they're trying to say mu equals 15. This one, the HO, the null hypothesis, happens to be the claim. Now the opposite of that would be not equal to 15. Okay, so that's your alternate hypothesis. And then the last one, a college board claims the majority of students support a ban on smoking. Okay, this one's a little tricky because a majority is more than half. Okay, so they're basically saying the board claims that more than half or greater than 50% of students support a ban on smoking. So P equals 0.5 is HO, and H1 is P is greater than 0.5, and that was the claim, okay, the alternate. Okay, so that's how you identify your null and alternative hypotheses when you read a question. Okay, one of these sentences will be part of the question. Okay, somebody's going to claim something, and that's how you organize your HO and H1. Okay, on the next page, okay, when we actually perform a hypothesis test, we always assume the null hypothesis is true. There's only two possible decisions. We actually reject the null hypothesis, or we fail to reject the null hypothesis. Okay, we either reject the null hypothesis or we don't. Okay, so those are the only two decisions you can make. Okay, now the issue is, since we always make our decision based on a sample, it's always possible that we make a mistake in our decision. Okay, so we have some errors that we can make. A type 1 error is that we reject HO when HO is really true. And a type 2 is that we fail to reject HO when HO is really false. Okay, so a type 1 is saying that we do not reject the null hypothesis. I'm sorry, I just said it backwards. A type 1 error is that we reject the null hypothesis when we shouldn't have. And then type 2 is that we fail to reject the null hypothesis when we should have. Okay, so the best way to think about this is like a courtroom example. Okay, so when you go to a trial, we always assume the defendant is innocent until enough evidence presented to declare him guilty or her guilty. Okay, what a type 1 error would be is rejecting that he is innocent when he really is innocent, which means you'd be sending an innocent person to jail. Okay, so the idea there is reject that he is innocent. So you're rejecting the null hypotheses. Well, remember, we're assuming the null hypothesis is true. So we're assuming he was innocent. And then we presented evidence, and the type 1 error is that we rejected that he's innocent when he really is innocent. Okay, and that would be a major mistake to make. They basically have innocent people sitting in jail, and that would be a very bad error. A type 2 error would be failing to reject that he's innocent when he is not innocent, which in this case would be setting a guilty person free. Okay, so we fail to reject he's innocent. Okay, so we're basically saying he's guilty when he really is not innocent. Okay, so we set a guilty person free. Okay, that's a bad mistake to make also. Now, most people would agree that a type 1 error is the worst, because then you have innocent people sitting in jail. And a type 2 error, although it's bad, a type 2 error isn't as devastating as a type 1 error. Okay, so looking at number 1, okay, that was just a basic one with the wait times at a restaurant. Okay, so going back to that example, okay, identify the type 1 and type 2 errors. Okay, so I just have them written out here. So if you want to pause the video, go ahead. For the sake of time, I'm going to move on though. Okay, they're pretty self-explanatory when you read those. Okay, so then we get to making a decision. Okay, so what we do is we find something called a critical value, which is just a z or a t score. Now there's a little symbol there, alpha, which I'll explain here. Okay, so you find a critical value for z or t and sketch the rejection region for HO. Alpha, okay, which is this little sideways fishy. Okay, that's not very mathematical, but that's how most people describe it. Okay, almost like an italicized lowercase a. Okay, it's alpha. It represents the maximum allowable probability of a type 1 error. And again, the idea there was a type 1 error is sending an innocent person to jail. Okay, we want that error to be very small. Okay, so alpha is going to be a small value, like 0.01 or 0.05 or 0.10. Okay, and then the second step, we calculate what we call a test statistic. Okay, so the idea is we have this maximum allowable error that we want to make, or the probability of that type 1 error, and then we're going to find a test statistic based on our sample data. Okay, so that's going to come from our sample. Okay, so it might be an X bar and an S, or maybe we know what sigma is. Okay, but again, that's going to come from sample data. And then if the test statistic lies in the rejection region, then we reject HO. Okay, we reject the null hypothesis. Okay, so how do we find our rejection regions? Okay, well, again, it looks kind of crazy, but it really isn't too bad once you understand it. There's 3 types of hypothesis tests. There's a left tail. Okay, so what we look at is a null hypothesis may be something like mu equals k. Okay, like mu equals 20, mu equals 5, mu equals some number. It could be p equals a number, like p equals 0.7, p equals 0.90. And then the alternative hypothesis for a left tail test is a less than. Okay, so when you say mu or p is less than a number, well, less than, we're going to shade to the left. Okay, so we draw our normal curve. We shade to the left. And alpha, okay, this symbol here is the area in that left-hand tail. Okay, and the idea is we're going to have a negative z or a negative t sub alpha value. Okay, so we're going to look those up on a chart. So if alpha is 0.05, we can find the z score or t score that has 5% to its left. Okay, if alpha is 0.01, we could find a z or a t score that has 1% to its left. And we know they're going to be negative z or t scores because 1%, 0.01, 5%, 0.05 to the left means we're way over on the left-hand side over here. Okay, so that's a left tail test, and you identify that by the less than symbol. And then we have a right tail test, okay, which is really just the opposite. Okay, so a right tail test, we recognize that by the greater than in the alternative hypotheses. And that means that alpha is the area to the right of a z sub alpha or t sub alpha value. Okay, and then we can have a two-tail test, which means we're shading both directions. Okay, and this one's a little bit different because alpha is your total area. Well, now we're split between two tails, so you have to divide that alpha by 2. So for example, if alpha is 0.05, so you want a 5% chance of making the type 1 error, you would take 0.05, divide by 2, and that'll give you 0.025 in each tail. So you're going to have the same z and t scores on either side, except one will be negative on the left side and the other positive. Okay, and the idea is going to be if our test statistic, okay, so the value from our sample, okay, we're going to collect sample data and find a z or a t score based on that sample data. If they fall in the shaded region, here, here, or here, or here, depending on the types of test, whether it's a left-tailed, right-tailed, or two-tailed test, that's when we reject HO, when our test statistic lies in the shaded region. Okay, and again, when we do an actual example of these, it'll probably make more sense. Okay, so suppose we have an alpha of 0.05. So the probability of sending an innocent person to jail, we want it to be 0.05 or 5%. Find the critical z value and sketch the rejection region for each test. So if we have a left-tailed test, okay, left tail means we're shading to the left. We have 5% to the left. So when we look up the z-score for that, well, the z-score that has 0.05 area to its left is negative 1.645. Okay, so the critical z-value is negative 1.645. Okay, and this is very similar to finding those values when we did the confidence intervals. Okay, it's nothing different right now. Right tail test, same thing because of the symmetry, except we get a positive critical z-value of positive 1.645. And then a two-tailed test, well, that's where you have to divide the 0.05 by 2 because we're in both tails. So if you look up 0.025, area to the left, you get negative 1.96, and then on the other side, positive 1.96. Okay, so there's your critical values that identify the rejection regions for HO. Okay, moving on to the next page. Okay, now suppose we have to use the t-values. Okay, and it'll be clear when we do some examples of when you use z and when you use t. It'll be similar to the confidence intervals. Okay, remember when you did confidence intervals, you used z when sigma was known, and you had a normal distribution, or n was greater than 30. You used t when sigma was unknown, and you had a normal population, or n is greater than 30. So to find the critical t-value and sketch the rejection region if alpha is 0.01, so for a right-tailed test, we shade to the right. And if you look up 0.01, okay, so alpha is 0.01, so that's why I put that down here. If you look up 0.01 area in one tail with n minus 1 degrees of freedom, so 29 degrees of freedom, you go to your tables, and that's a t-value of 2.462. Okay, and I'm assuming we can do this now because you did the same thing with the confidence intervals. Okay, left tail test, because of the symmetry of the t distribution, it'll be the same t-value except negative. And then a two-tail test, well, now we have 0.005 in one tail because we divide 0.01 by 2. Or you could look at 0.01 in two tails with 29 degrees of freedom, and you get the critical t-value of plus or minus 2.756. Okay, so make sure you can look those up in the tables. Okay, so that's how we find the rejection region. Okay, and then the next step is to actually calculate a test statistic. Okay, now the idea is that we're going to collect a sample of data, and whether we're looking at a proportion, a population proportion p, or mu, we have different formulas for those. Okay, now, same idea as with the confidence intervals. We have a formula, except now they're a little bit different. Okay, z, anytime you're looking at a p, okay, so you're looking at population proportion, you're always going to use z. When you're looking at the mean, mu, that's when sigma is known. Okay, so that's important. And then a mean mu, sigma is not known. That's when you use the t. When sigma is known, you use the z. Okay, so those formulas you'll be given. You don't need to memorize those. They'll be given to you. Can you notice the form of the mu formulas are the same? X bar minus mu are the numerator of each, and then the standard deviation divided by square root of n. Well, S is the sample, sigma is the population. Okay, so before we get into an actual example of the entire hypothesis test, okay, if we look at, suppose we collected data and we end up with a z-score of -2. Okay, so suppose you were looking at, let's just say, a mean, and you use this formula and you end up with z equals -2 after you plug the values in for x bar, mu, sigma, square root of n. So we get a z-value of -2 for a left-tail test. Decide whether to reject HO if the level of significance is, well, if we have alpha is 0.01. Okay, so what we need to do is we have 0.01 area to its left, because we're a left-tail test. When you look up an area of about 0.1000, you get a z-score of -1.28. Okay, that is the z sub alpha value. Okay, and then what you look for is our test statistic ended up with -2 for z. So we are over here in the shaded region. So we're to the left of -1.28. So what does that tell us? We're in the shaded region, so we reject HO. Okay, so our decision would be to reject HO. Now suppose alpha is 0.05, okay, which is basically saying instead of having 10% to the left here, now we're going to go half that and say 5%. So we're going to move over a little bit, okay, like shift that shading to the left some, and there our z-score is -1.645. Okay, oops, I should have put a z there. So this is our z sub alpha value. That's your critical number. And -2, well, notice how we got a little bit closer to -2, but we're still not quite there. So we still reject HO. That's a decision we would make. Last one, suppose alpha is 0.01. So now we're going even farther to the left with that shading. So now we only have 1% shaded to the left. So now that gives us a critical z-score, okay, again, z sub alpha, of -2.33. Well, now we notice -2 is not in the shaded region anymore. So what that tells us is that we fail to reject HO. Okay, and then the next thing we get to is actually making our decision. Okay, now this is going to have to do with the claim, and I'm not going to spend much time on this. That'll be in the next video. But we have a claim was either HO or H1. Okay, so when you go back to that first page, on a few of these, after we wrote hypotheses, like in the part A, our claim was H1. Down in part D, our claim was HO. Okay, so the claim can be either hypotheses, HO or H1. Okay, so the idea here is, since our claim could be either one, HO or H1, our decision is to reject HO or fail to reject HO. Okay, so those are the two decisions we can make. Okay, so on that last page, we either failed to reject HO or we rejected HO. Okay, and then there's these 4 different possibilities of what that's telling us about what we say about our claim. Okay, and I will get to that when we actually do an example, because me just reading those I don't think will mean too much until we see an actual example. Okay, so in the next video, we'll look at actually doing a hypothesis test. Okay, there's 6 basic steps. We just did every step. Okay, now it may not seem like it, but we just actually worked our way through what you'd have to do for a hypothesis test. Okay, so we'll do number 6 on the next video.